All right, now that you have been working with the simulator and kind of see what happens when electronegativities change, and how there are dipoles for bonds and or molecules, what you're going to do on your Lewis structure sheet is you are going to show the dipoles for the molecule, or sorry, for each bond, if there are any, and then decide if you think the molecule or ion is polar or nonpolar. So you can just put a P or NP for the polar or nonpolar, but for the dipoles on the bonds, you need to um, draw them all. So for instance, you have a Lewis structure for Pi3 that looks something like this. Every bond that is polar will have a dipole drawn on it. So if you look your electronegativity chart, you're going to see that phosphorus has a electronegativity of 2.1 and iodine has electronegativity of 2.5. If the difference in electronegativity is zero point 0.4 or greater, actually it's 0.4 to 2, but what we'll see with the non-metals is that they're going to be between, oops, I forgot an iodine here. Um, that if they're between 0.5 and 2, but you're going to see with the non-metals, we're not going to go over 2. But if it's more than 0.4, man, I'm screwing up my numbers. If it's more than 0.4 or more, 0.4 or greater, then we're going to draw a dipole, and that means that there's a polar bond. So here, there's a polar bond. I am pointing the arrow towards the more electronegative and putting a positive on the other end. This right here is a polar bond between phosphorus and iodine. Right here, it is a polar bond. So every bond gets a dipole drawn on it if it is polar. And how you decide if it's polar is if the difference in electronegativity is 0.4 or greater. Then you need to think about the shape. In reality, for Pi3, since the shape is trigonopyramidal, you can kind of think of it as like this. And I know that we could kind of draw them as being like coming out at you, and then we could kind of look at this being back into the paper, but it's three-dimensionally, it's really more like this. Man, that's supposed to be an eye. Oofty. So in reality, all these negative charges, and as your um, simulator showed, and you don't need to show these, but in reality, there's a partial negative charge here and a partial positive charge here. This is just a delta sign. It means partial. There's not a full positive or negative because it's not ionic, but there are partial negatives. So this whole bottom of this molecule is negatively charged, and the top of the molecule, the phosphorus part, is positively charged. So when one side of the molecule is negatively charged, the bottom here is negative, and the top is positive, that is what is called a polar molecule. So that molecule is polar because there's a negative side to it, and bottom part of it is negative, and the top part of it is positive. So that one is polar. What I want you to do with your groups now is do this with all of the structures on here. Draw dipoles if they exist. For instance, if you're like, well, how do I know if they exist or wouldn't they exist? If you look at your electronegativity chart, you should see a difference of 0.4 or greater. If there is not a difference of 0.4 or greater between two atoms, you do not draw the dipole. And that automatically means the molecule is nonpolar or ion, like this is an ion. So the only way you can have a polar molecule is if you have polar bonds. But just because you have polar bonds doesn't mean for sure that it is a polar molecule. Sometimes these dipoles can cancel each other out. So you really need to think about the shape. Is the shape allowing you to have one side of the molecule positive and the other side negative? You should come with this to class next time with it all complete with dipoles and P for polar and NP for nonpolar. And we'll go over it when we come back together. But that is what you should be writing down next.